Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like distributed memory parallel programming with MPI, message passing, message and point-to-point communication. Let's get started. Slide 1. Distributed memory parallel programming with MPI. Let's begin with an important concept in high-performance computing, distributed memory parallel programming with MPI. First, distributed memory parallel programming is a model where each processor or core has its own private memory. Unlike shared memory models, no memory is directly shared between processors. Now, MPI, which stands for Message Passing Interface, is a widely used library standard that allows communication between these distributed processes. Each process runs independently, and if they need to exchange data, they do so by sending and receiving messages. A very important term here is process rank. It's like a unique ID given to each process so they can identify and communicate with each other. This model is extremely scalable. We can run programs on hundreds or even thousands of processes, which makes it perfect for large scientific simulations, like weather forecasting or molecular dynamics. So, MPI allows efficient collaboration among distributed processes without relying on shared memory, making it essential for large, distributed systems like clusters and supercomputers. Slide 2. Understanding message passing in MPI. Next, let's talk about message passing, which is the core mechanism of communication in MPI. When we say message passing, we mean that processes explicitly send and receive data to work together. In MPI, messages are the units of data exchanged between processes, and functions like MPI_send and MPI_receive are used to perform these exchanges. Message passing in MPI can be either blocking, where a process waits until the communication is complete, or non-blocking, where a process can continue working while data is being transferred. Another critical feature is message tagging, which helps processes to correctly identify incoming data, especially when multiple messages are in transit. The message passing model requires careful planning because each process has its own memory, and there is no automatic data sharing like in Open. For example, if process 0 calculates a result that process 1 needs, process 0 will send a message containing the data to process 1 using MPI_send. Thus, message passing allows distributed processes to collaborate, share work, and synchronize their actions. Slide 3. Message and point-to-point communication in MPI. Now let's focus on point-to-point communication, which is the simplest form of communication in MPI, involving just two processes. Two fundamental MPI functions are MPI_send, to send data from one process to another, MPI_receive, to receive data. In point-to-point communication, both sender and receiver must be clearly identified, including the data's size, type, and tag. Blocking communication means the process waits until the message is sent or received, ensuring synchronization. In contrast, non-blocking communication, like MPI_send and MPI_receive, allows processes to continue working while waiting for communication to complete. Tags are like labels on messages, helping processes handle multiple communications efficiently. Point-to-point communication is essential for fine-grained control over who sends and receives data. For instance, if process 2 computes a value that only process 5 needs, point-to-point communication allows them to exchange data without involving others. Thus, this method provides flexible and controlled data exchange between specific processes in a distributed system. Slide 4. Advantages and disadvantages of MPI, distributed memory model. Let's analyze the advantages and disadvantages of using MPI and the distributed memory model. Advantages. 1. MPI allows us to use multiple computers connected over a network to solve large problems. 2. Since each process has its own private memory, there are no issues with shared memory conflicts. 3. MPI is highly scalable, making it suitable for systems with thousands of processes. 4. It offers fine control over communication, helping optimize data flow and efficiency. 5. Heterogeneous systems, different hardware types, can work together using MPI. 6. MPI is ideal for problems where data is naturally distributed, like large simulations. 7. Works well in cloud and cluster computing environments. 8. Supports both fine and coarse-grained parallelism, adaptable to various problems. 9. Well-documented standard library, widely supported in HPC systems. Disadvantages. 1. Explicit communication makes coding complex, requiring more effort to write and manage programs. 2. Communication overhead can reduce performance if data is exchanged too frequently. 3. Debugging message passing errors like mismatches and deadlocks is difficult. 4. Not efficient for small-scale parallelism, where simpler shared memory models may be better. 5. Load balancing and data distribution need to be handled manually. 6. If communication patterns are incorrect, entire programs may halt. 7. Not as intuitive as shared memory models, requiring good understanding of distributed computing concepts. 8. MPI may be hard to port to non-cluster environments. 9. Higher initial programming effort, but beneficial for large systems. So, while MPI is powerful and scalable, it requires careful programming and planning to be effective. Slide 5. Differences between shared memory and distributed memory, MPI versus Open. Now let's discuss the differences between shared memory, Open, and distributed memory, MPI, very important to understand when choosing a parallel programming model. 1. Memory type. Open uses shared memory, so all threads access the same memory space. MPI uses distributed memory, where each process has its own separate memory. 2. Communication. Open does not need explicit communication, threads share data directly. MPI requires explicit message passing to share data. 3. Programming complexity. Open was simpler to program, while MPI is more complex due to manual communication. 4. Scalability. Open was limited to systems with shared memory, like a single multi-core machine. MPI can scale across many computers, making it suitable for large clusters. 5. Synchronization. Open provides built-in synchronization, like critical sections. MPI synchronization must be handled manually through messages. 6. Hardware support. Open works on one machine with multiple cores. MPI works across multiple machines or nodes. 7. Suitable problems. Open was best for small to medium parallel problems. MPI is used for large distributed problems, like scientific computations. 8. Data management. Open handles data sharing automatically. MPI requires the programmer to manage data distribution and communication. 9. Fault tolerance. In Open, if one thread fails, it may crash the program. MPI can be designed for some level of fault tolerance if a process fails. So, depending on the problem size and system architecture, you choose between Open and MPI. Slide 6. Challenges and best practices in MPI programming. Finally, let's explore challenges and best practices in MPI programming. Challenges. 1. Message passing errors, like mismatches in send and receive calls. 2. Deadlocks, where processes wait indefinitely for messages. 3. Uneven workload distribution, causing some processes to be idle. 4. High communication overhead, which can slow down programs. 5. Difficulties in debugging distributed processes. 6. Maintaining correct message tags and order. 7. Handling large data transfers efficiently without overloading the network. Best practices. 1. Minimize communication, share only necessary data. 2. Use non-blocking communication to avoid idle time. 3. Always tag messages properly and ensure the correct order. 4. Avoid deadlocks by following consistent communication patterns. 5. Use collective operations, like broadcast, reduce, for efficiency. 6. Start with small programs to test communication before scaling. 7. Profile performance to find and fix bottlenecks. 8. Distribute work evenly to avoid some processes doing all the work. 9. Align communication design with hardware and network topology for optimal performance. By following these practices, MPI programs can be made efficient, scalable, and reliable for distributed computing tasks.